Hello everyone. Hello. Good afternoon. We are studying electrochemistry, and in that electrochemistry topic now we will see why electrode potential is developed. What is mean by electrode potential? Why that electrode potential is developed when any metal rod or metal electrode is dipped in its ion containing solution. What is the theory behind that electrode potential? Okay, now if we consider any electrode dipped in its ion containing solution, okay, see here, if we dip electrode in its own ion containing solution, then what happens? This metal rod or metal wire, that electrode, has two types of tendencies. In one tendency, this metal goes in the solution. Metal goes in the solution as positively charged ions, leaving behind electrons. Electrons are on same electrode. Means if we consider that electrode picture, here what happens? Electrode having negatively charged electron on it, because electrode material is going in the solution as metal ion, leaving behind that electron on same electrode. Now these electrons are on that electrode, it is negatively charged and it is dipped in solution, due to which positively charged ions gather around it, and there is a formation of electrical double layer, and this electrical double layer is responsible for production of potential, or it is responsible for electrode potential. Now in vice versa, if we consider some another electrode dipped in electrolyte solution, then sometimes what happens, that material has a tendency to deposit from the solution. Suppose copper electrode is dipped in Cu2 plus ion containing solution. Then here what happens, copper 2 plus ions from solution has a tendency to deposit. Now for deposition of copper 2 plus, it requires 2 electrons. Means electrons are withdrawn from the electrode. Negative charge is withdrawn from the electrode. That's why which charge is coming on this electrode? Positive charge. This means this electrode is becoming positively charged, and simultaneously negatively charged ions from solution gather around it. There is again formation of electrical layer as like a condenser, and this electrical double layer, there may be tendency of oxidation or may be tendency of reduction. This loss of electron is the oxidation, gain of electron is the reduction. Whatever may be the tendency, may be tendency of oxidation, may be tendency of reduction, maybe substance go in the solution, may substance from solution deposit on the electrode. In both cases there is a formation of electrical double layer, and this electrical double layer is responsible for electrode potential. There is a development of potential on that electron. Okay, now we will see how that electrode potential is determined by using Nernst equation. Suppose we consider any electrochemical cell, or suppose certain redox reaction, A gives B. Suppose this is a redox reaction, whatever may be. One substance, suppose consider A plus B gives C plus D. This is the redox reaction. What is meant by redox reaction? The reaction where reduction as well as oxidation takes place simultaneously, known as redox reaction. Now what happens in that redox reaction? In electrochemical cell, electron is transferred. Means there is some work done. We call it as a electrical work done. And this work done, thermodynamically this work done, delta G is nothing but W max. We will see it in thermodynamic topic. Okay, delta G is W max, and we in this redox reaction it is the electrical work done. Okay, this delta G is nothing but the electrical work done, but thermodynamically this delta G is equal to minus NEF. Delta G is equal to minus NEF. Now what is this F? F is ultimately in electrochemistry, F is Faraday constant. F is Faraday constant whose value is nearly taken as 96,500 Coulomb. Okay. Now E, what is E? We are using this equation in electrochemistry. That's why E is nothing but the cell potential or EMF of that particular cell. And what is N? It is not number of moles. Here in electrochemistry, it is considered as a electrons, number of electrons per mole or number of electrons per atom. For example, if we consider the oxidation of copper, Cu2 plus 2 electron. If we simply consider oxidation of copper, Cu gives Cu2 plus 2 electron. How many number of electrons are here removed per metal ion? 2. 2 electrons are removed per metal ion. That's why here N is 2. If we consider mole, then 2 moles of electrons are removed from 1 mole of copper atom. Okay. Now this N is the number of electrons transferred per metal ion. This equation is useful for derivation of Nernst equation. This Nernst equation gives the potential developed in cell as well as in electrode. Okay. Now we will derive the equation, Nernst equation. We will see how this potential developed is determined for a particular cell by using Nernst equation. Now consider a general reaction. A plus B gives C plus D. Okay, in some reaction what happens, there are stoichiometric coefficient, maybe 2A plus 3B, whatever may be. That's why in general we will consider XA plus YB gives ZC plus WD. Here X, Y, Z, W, these are stoichiometric coefficient used for balancing of that particular reaction. Okay. Now X, Y, Z, W, these are coefficients, stoichiometric coefficient. We are considering a general reaction. A plus B gives C plus D. And X, Y, Z, W, these are stoichiometric coefficients. Okay. Now, if we consider the delta G of this reaction, thermodynamically again, we have to take this equation directly. We will see in thermodynamic topic. Okay. Here delta G for a particular reaction is given by delta G is equal to delta G naught plus RT ln Q. This delta G is given by equation delta G is equal to delta G naught plus RT ln Q. What is this delta G? Is the change in free energy for a particular reaction. Delta G naught, it is the change in free energy under standard conditions. Means if we consider gas, the pressure should be 1 atmosphere. If we consider solution, the concentration should be 1 mole per dm cube. Under that particular conditions, under standard conditions, the change in free energy is written as delta G naught. plus RT. R is a gas constant, T is the temperature in absolute scale in Kelvin, and Q, instead of Q it is written as QA. It is written as QA. It is the reaction quotient. QA is the reaction quotient. Reaction quotient. How it is determined? This reaction quotient is equal to, or it is as like equilibrium constant. How equilibrium constant is written? It is the ratio of concentration of product to the concentration of reactant. If we take activity, then equilibrium constant is the ratio of activity of product upon activity of reactant. But this equilibrium constant is applied only when equilibrium is attained. During reaction we can't apply equilibrium constant. Okay. Now during reaction we will consider this reaction quotient QA. If reaction is going on, we have to write QA. It is as like equilibrium constant. That's why, how will you write QA here? QA is equal to activity of product upon activity of reactant raised to suitable power, raised to its coefficient. Means it is the ratio. Now take the product, activity of C into activity of D raised to suitable power, raised to this coefficient. Therefore, QA is equal to activity of C raised to Z into activity of D raised to W upon, this is the activity of product upon activity of reactant, means activity of A raised to X into activity of B raised to Y. Okay, this is the reaction quotient, and throughout this topic you have to write this QA, reaction quotient, activity of product upon activity of reactant. If more number of products are there, then take their products. If more number of reactants are there, take product of activity. Okay, this is the reaction quotient. Okay, now again we know this delta G. What is the value of delta G? Already we have seen delta G is nothing but minus NEF. Delta G is equal to minus NEF. Okay, now what is delta G naught under standard condition? Faraday constant is constant. Again here number of electrons, they are again constant, they are not changing with condition. Therefore delta G naught is minus N E naught F. E naught is the standard EMF. EMF measured under standard conditions. Okay, plus RT ln QA. QA is the reaction quotient. You know how it is determined. Okay, now to this equation divide by minus NF. Each term of this equation is divided by minus NF. Divide by minus NF. Then what will be the equation? Just divide each term by minus NF. Then it will be again minus NF divided by this term by minus NF, this term by minus NF. Now what is getting cancelled? Minus minus get cancelled, N get cancelled, F get cancelled. Then what will be the equation? E is equal to, here again minus minus, N F get cancelled, E is equal to E naught. Here the sign will be minus. E is equal to E naught minus RT upon NF log of no log. It is ln of QA. Now if we take log here, what will happen? What will be the equation? E is equal to E naught minus, if we consider ln to log, then what is done? Minus 2.303 RT upon NF log. Now here log QA. This is the Nernst equation for either electrode potential or cell potential. If you are determining or if you are applying it for electrode potential, then write here electrode. Electrode potential is equal to standard electrode potential minus 2.303 RT upon NF log of QA. Yes, if we are applying same equation for cell potential, then instead of electrode write cell. E cell is equal to E naught cell minus 2.303 RT upon NF log Q. Now what happens in the same equation here? 2.303, see this quantity, 2.303 RT upon NF. 2.303 is constant, R is gas constant. If we consider temperature as a 298 Kelvin, now at 298 Kelvin temperature, means temperature we are fixing, we are considering a constant temperature. In this equation, 2.303 is constant, R is constant, T is constant, F is Faraday constant. That's why all these terms are constant. 2.303 RT upon F remains constant at 298 Kelvin. This value 2.303 RT upon F, the value of this constant quantity at 298 Kelvin temperature is 0.0591. Therefore, this Nernst equation becomes, final Nernst equation becomes simplified Nernst equation. It will be E is equal to E naught minus 0.0591 upon N log of QA. You can put the value of QA here for a particular reaction. This is the Nernst equation simplified form. This equation and this equation both are Nernst equations for either electrode potential or cell potential. Got it? Yes. Now we will see one example, two examples of this Nernst equation, how this equation is applied. Now consider a simple reduction reaction. Zn2 plus takes 2 electron, gives Zn. This is a simple reduction reaction. Now for this reaction also EZn. Here we are taking zinc electrode, that's why you have to write EZn. Or in another way also EZn2 plus Zn. This is the perfect notation. EMF of Zn2 plus Zn electrode is equal to E naught. E naught of Zn2 plus Zn electrode minus, we will take a simplified equation, 0.0591 upon N. N means number of electrons transferred per ion. 2 electrons. That's why we will take here 2 and log of QA. QA is the reaction quotient, activity of product upon activity of reactant. Okay. Now this equation is used for determination of electrode potential or cell potential. Okay. Got it? How the electrode potential is determined by using Nernst equation. Yes, okay, thank you.